our objective is to provide a basic understanding of key steps of oil and gas exploration and production from a scientific and technological point of view. We will start by briefly describing what we need to know about the rock types for this objective. Learning objectives for the rock type section are that you must be able to define and recognize the differences between igneous, metamorphic, and sedimentary rocks. Also, you must be able to define shale, carbonate, and sandstone, and their importance for oil and gas accumulations on a commercial scale. The second part is where we will talk about source rock and oil and gas traps. The learning objectives are to define source rocks, oil migrations, oil traps, and reservoirs. These are key components for large accumulations of conventional oil and gas in the subsurface. Rock types. Igneous rocks are formed from the cooling and crystallization of magma below the Earth's crust. When magma cools slowly within the crust, it forms coarse crystalline rocks such as granite and gabbro. Metamorphic rocks are formed by the modification of pre-existing rocks by high temperatures and/or high pressures. Sedimentary rocks are formed from the breakdown of pre-existing rocks, igneous, metamorphic, and sedimentary. They are formed by both the direct deposition of fragments of pre-existing rock and the precipitation of their solutes. We'll come back to the definition of deposition and precipitations. Igneous and metamorphic rocks represent 95% of the crust. Igneous rocks represent 100% of the mantle. 75% of Earth's solid surface, or land, is sediments and sedimentary rocks. Please note that igneous rock can change into sedimentary or metamorphic rock. Sedimentary rock can change into metamorphic or igneous rock. Metamorphic rock can change into igneous or sedimentary rock. That's what the rock cycle is about, and we will talk about this next. Let us connect these three types of rocks through what is generally known as the rock cycle. The rocks of the Earth's crust are constantly being recycled. Magma solidifies to form igneous rocks. If igneous rocks are exposed at the surface, they weather, and weathered rock fragments are transported and sediments are deposited and lithified into sedimentary rocks. This process illustrates the transformations from igneous rocks to sedimentary rocks. If the igneous or sedimentary rocks are subjected to temperatures and pressures that exceed those under which they have been solidified, they may undergo changes to form metamorphic rocks. This process illustrates the transformations from igneous rocks to metamorphic rocks. We can explain any path of the rock cycle using the methodology of these two examples. Weathering is the term that is applied to the processes that break down rocks at the surface of the Earth. The weathered mantle is subject to erosion. The rate of erosion varies widely across the Earth. It is normally highest on steep mountain slopes and lowest on horizontal slopes, where the weathering mantle can thus become very thick. Rocks are weathered in upland areas, then eroded and transported downslope and deposited in low-lying areas in both continental and marine environments. As far as oil and gas are concerned, sedimentary rocks are very important. Sedimentary rocks tend to be deposited with voids between sediment particles. Thus, most petroleum reservoirs are found in the coarser sediments. Fine-grained sediments serve as impermeable seals to petroleum migration and also as petroleum source beds. So, in petroleum industry, you will hear more about sedimentary rocks than any other rocks. Sediments are generally classified by grain size. For example, clay, claystone, silt, siltstone, sand, sandstone, gravel, and conglomerate. They are also classified by their chemistry, such as shale, carbonate, sandstone, and evaporites. Let me repeat this. This is very important. Sediments are generally classified by grain size. For example, clay, claystone, silt, siltstone, sand, sandstone, gravel, and conglomerate. They are also classified by their chemistry, such as shale, carbonate, sandstone, and evaporites. Shale is composed principally of clay minerals. Sandstone is composed principally of quartz. Carbonate rocks are composed primarily of carbonate minerals, with the two main types of carbonates being limestone and dolomite. Evaporites are salts formed from the evaporation of seawater, such as gypsum, anhydrite, halite, and more. Shale, sandstone, and carbonates make up about 99% of all of the sedimentary rocks, with shale being the most abundant and carbonate the least abundant. Yet the oil amount in carbonate petroleum reservoirs is almost equivalent to the oil amount in sandstone petroleum reservoirs. Keep this figure in mind. We'll come back to it. It tells us about unconventional oil and gas related to shale. Let me repeat to you that shale, sandstone, and carbonates make up about 99% of all the sedimentary rocks. Carbonate rocks are a class of sedimentary rocks composed primarily of carbonate minerals. The two major types are limestone and dolomite. Sandstones are also sedimentary rocks, composed mainly of sand-sized minerals or rock grains. Again, this partition is about conventional oil and gas. It drastically changes if we consider unconventionals as shales contain oil and gas. Notice that more than 75% of sedimentary rocks do not contain oil and gas. Let's now turn to source rocks of oil and gas. We'll start by recalling again that petroleum, that's oil and gas, is a naturally occurring flammable liquid. It is formed from organic matter, that's tiny plants, algae and bacteria, or plankton, that lived in the ocean millions and millions of years ago. As living organisms, they absorbed energy from the sun, which was stored as carbon molecules in their bodies. When they died, they sank to the bottom of the sea. Vast quantities of these remains long ago settled on sea or lake bottoms, mixing with sediments and being buried under special anoxic conditions. As further layers settled to the sea or lake bed, intense heat and pressure built up in the lower regions. Burial, and thus the heating of such organic matter, induces reactions leading to the generation of gas, then oil and gas, and finally gas alone as the temperature and residence time at high temperatures increase. Let's talk about the golden zone. Temperature controls oil and gas generation. Nadeau and his co-workers show that most of the hydrocarbons in a sedimentary basin, both oil and gas, are located at a depth at which the temperature is between 60 and 120 degrees Celsius. This is the golden zone. The golden zone lies at different depths in different basins, depending on the geothermal gradient. It is, for example, shallow in the Bombay High of India and deep in the Gulf of Mexico. Note that large accumulations are between 80 to 100 degrees. Let us make it clear that temperature alone will not allow us to find oil. It will only confirm the likelihood of your findings of oil and gas. The rocks from which the generation of oil and gas takes place are known in petroleum geology as source rocks. Source rocks are generally sedimentary rocks, typically shale or limestone, that are rich in organic matter. After we have defined all the components of large oil accumulation, the notion of source rocks will be clear. The oil and gas formed deep in the subsurface tend to rise toward the Earth's surface because they are less dense than water and most surrounding rocks. Their upward movement is known as migration. Some oil and natural gas has migrated all the way to the surface and escaped. Other migrations of oil and gas are halted by impermeable rocks known as seals or cap rocks. Seal rocks are a critical component of large oil accumulations. Seals tend to be fine-grained or crystalline low permeability rocks such as mudstone or shale, cemented limestone, chert, anhydrite, and salt or halite. Seals can also develop along fault planes, faulted zones, and fractures. Again, let me repeat that seal rocks are a critical component of large oil accumulations. The presence of seals is critical for the accumulation of petroleum in commercial quantity to occur in the subsurface. In the absence of seals, petroleum will rise to the Earth's surface and be destroyed. Although seals are critical for the accumulation of petroleum in commercial quantities, they are not leak-proof. However, their large thickness and lateral extent minimize the leakages. The most common lithology that forms a petroleum seal is mud rock. Mud rocks are composed of either carbonate or siliclastic minerals, or both, and mud rock sequences are often thick, or greater than 50 meters, and laterally continuous, or greater than 10 kilometers squared. Examples of mud rock seals are found in the Gulf of Mexico, the Niger Delta, the Northwest Australian Shelf, Northwestern Europe, the North Sea, and Southeast Asia. Halite forms part of the sealing lithology in many of the large Middle East petroleum accumulations. In addition to a seal, we need a petroleum reservoir in order to have accumulation of petroleum in commercial quantities. That is, porous rock. This is a rock capable of holding petroleum. Impermeable rock. This is a rock which permits the flow of petroleum, in which oil accumulates. Therefore, reservoir is a central component of large oil accumulation. These reservoirs are typically sandstones or carbonates. The goal of petroleum exploration is to find present-day traps whose seals are intact and whose reservoir rocks are 1. Sufficiently porous to contain commercial quantities of petroleum, and 2. Sufficiently permeable to allow them to flow fast enough toward production wells. So petroleum is always inside the pores of the rock. We must press the rock to make sure the pores are connected or permeable to extract the oil. Let's repeat that. So petroleum is always inside the pores of the rock. We must press the rock to make sure the pores are connected or permeable to extract the oil. Here's an illustration of the prerequisites for hydrocarbon trap. Although there are many trap configurations, the one shown here, an anticlinal fold, is perhaps the simplest. The single-headed arrow depicts the primary migration of oil and gas from a maturing source rock into an overlying sandstone reservoir. Please take the time to identify the source rock in this picture. Let's talk about petroleum traps, starting with reservoir rocks and hydrocarbon migration. Reservoir rocks must have high porosity or open spaces in the rock that stores fluid. Reservoir rocks must also have permeability, which is the ease of fluid movement through pore space. Oil and gas migrate from source to reservoir. Less dense than water, they tend to rise. Migration is promoted by fractures in rocks. It is important that you master these notions, porosity and permeability, and that they are central in the discovery of a large accumulation of gas and oil and of the production of oil and gas. Let me redefine them for you. Porosity is open space in the rock that stores fluid. Permeability is the ease of fluid movement through pore space. A sill is a low permeability rock layer above a reservoir. A trap is a geological configuration that holds oil and gas. Trap geometry is crucial for fluid collection. This picture shows examples of geometries that allow you to hold oil. At A, you have the anticline trap, just like in the Middle East. At B is the fault trap, which are like most of the small deposits around the world. At C is the salt dome trap, just like in the Gulf of Mexico. And D is the stratigraphic trap. In stratigraphic traps, they're caused by deposition or erosion. They include traps which are not associated with unconformities, such as channels, barrier bars, and reefs, and those associated with unconformities, such as on-lap pinch-outs and truncations. Now that we have described traps and sill rocks, let's complete our description of oil and gas migrations. Notice that petroleum migrations, that is the process whereby petroleum moves from its place or origin, the source rock, toward the Earth's surface, are generally divided into 3 stages. 1. Primary migration, or the expulsion of petroleum from the source rock. 2. Secondary migration, or the journey from the source rock to the trap. And 3. Tertiary migration, or the leakage and dissipation of the petroleum at the Earth's surface. Primary migration is understood to occur when the petroleum volume in the source rock matches the volume of pore space in the source rock. That is, when the source rock is fully saturated with petroleum. Secondary migration takes petroleum from the source rock to the trap via carrier beds. On its escape from the source rock, petroleum is dispersed over a large area. By the time petroleum reaches relatively restricted areas of a trap, it can occupy more than 90% of the pore volume in the reservoir. Secondary migration is arrested once the migrating petroleum enters the trap. Disruption or overfilling of the trap can lead to remigration of the petroleum to upper structures under the same secondary migration process. Such secondary migration ends when petroleum approaches the Earth's surface. Tertiary migration includes leakages, seepage, dissipation, and alteration of petroleum as it reaches the Earth's surface. Leakage or movement of water and the hydrocarbons out of the trap into the surrounding rocks and possibly eventually to Earth's surface. Note that the endpoint of primary migration, which is also the starting point of the secondary migration, is still poorly understood in science. So, how do we find oil and gas? One can use what you have learned in this class in various forms to find oil. Basically, we are talking about sill rocks, reservoir rocks, source rocks, petroleum traps, oil migration, temperature zone, and even plate tectonics, which we learned about in previous classes to find oil. Here are 3 examples. In one example, you find oil by locating the sill rock and locating the petroleum trap. Locating the source rock and golden zone are optional. However, your accuracy of finding oil are improved with their use. In the next example, you are finding oil by locating the source rock and identifying the migration path. Locating the sill rock and the golden zone are optional in this example, but again, they improve the accuracy of finding oil, much like in the previous example. In the last example, you are finding oil with tectonic plate theory, which we've learned in previous classes. Suppose that you know that there is oil somewhere. We can use the Pangea map to discover oil in other oceans and continents. Then the locations of seal rocks and petroleum traps allow you to confirm new findings. Again, it is optional for you to locate the source rock, porous and permeable rock, and golden zone to improve your accuracy of finding oil. So for the estimation of oil and gas reserves, you have to 1. Locate the reservoir, 2. Porous and permeable reserve rock, and 3 is optional, but you can locate the golden zone or petroleum temperature window. In summary, to have a commercial petroleum prospect, several requirements must be met. There must be 1. A petroleum source rock, 2. A reservoir rock, and 3. A seal. Petroleum migrates from the source rock to the porous and permeable reservoir. The petroleum is trapped in the reservoir by the seal rock. Now we will conclude this section with a quiz. The question is as follows. Can we grab oil and gas from a source rock directly? Now we're back for the quiz. The question was, can we grab oil and gas from source rock directly? The answer is, in theory, yes. In practice, it is a great challenge because source rocks are very deep, at very high temperatures and pressure. Moreover, the reservoirs are very heterogeneous for oil production.